In this video, I'm going to go over some tips to help you analyze RC circuits, and we'll go through a couple examples. First, let's talk about capacitor behavior in an RC circuit. The first thing is that an uncharged capacitor doesn't really function any differently from bare wire. In other words, it doesn't affect or impede the flow of current through that part of the circuit. Mathematically, what we're saying is just that Q is equal to C times V, and so if there's no charge on the capacitor, then there's no voltage across the capacitor. For example, consider this circuit with a battery connected in series to a resistor, an uncharged capacitor, and a switch. Right now, nothing will happen. The circuit is incomplete, right? It's an open circuit because the switch is open. So there will be no current across the resistor, which means there'll be no voltage across the resistor. There'll be no charge on the capacitor because we started out with no charge and because no current can flow, which means there can be no separation of charges between the two plates. Now let's say that we close the switch at time t equals 0. It takes time for a capacitor to charge up, so right after the switch is closed, there's still no charge on the capacitor, which means there's no voltage across the capacitor. And so if we use the loop rule on the circuit, we'll find that the voltage across the resistor has to be equal to the voltage across the battery. This is just as if the capacitor wasn't even there. In fact, we find that the current through the circuit is just going to be the voltage across the battery divided by the resistance of the circuit. Now, this is only for t equals 0. This is for the moment after the switch was closed. So what's going to happen after we wait a while? Well, remember, a capacitor is technically a break in the circuit. There is a gap over here across which current doesn't flow. So as our current, our conventional current, travels or flows clockwise, it's going to result in a buildup of opposite charges on either side of the plate. As charge travels from one side of the capacitor to the other. And again, it cannot keep going across like it would in a traditional resistor circuit. It's actually blocked. And so this capacitor is going to charge up. This is going to change our loop rule. Instead of the uncharged capacitor having 0 voltage across it, now our capacitor will have charge on it, which means there will be some voltage across it, and we can represent that as Q over C. Naively, it looks like we have two unknowns in this equation, right? We don't know the current, we don't know the charge, and there aren't any additional equations. There are no junctions, and there are no additional loops that we can make use of. But Q and I are not actually independent of each other. If you recall, the current can be expressed as the rate of change of charge over time. This is the same equation that we saw in the previous video. I solved it there. I'm not going to go through that again, not for this particular circuit. But what we can talk about is what is going to happen after we wait a very long time. Well, eventually, there will be such a buildup of charges on the capacitor that it will obstruct any further flow of charges in the circuit. This battery wants to push positive charges in the clockwise direction, but I have this buildup of positive charges on the top plate of the capacitor that will oppose that current. Likewise, the negative charges will also oppose that current. That means that after you wait a long enough amount of time, you've essentially stopped the flow of current entirely. There's been such a separation of charges on the capacitor that the voltage across the capacitor, due to its increasing charge, will eventually equal the voltage across the battery. And when that happens, the capacitor stops all flow of current. So mathematically, after a long period of time, or a long period of time in this context means an amount of time much greater than the time constant RC, we'll have no current through our circuit, which means if we look at our loop rule again, there will be no voltage across the resistor. There will be a voltage across the capacitor. It will simply be equal to the voltage of the battery. In other words, in this circuit, when the capacitor is fully charged, its charge is simply equal to the product of the battery's voltage, or EMF, times the capacitor's capacitance. And again, once the capacitor is fully charged, it means that the current through the branch with the capacitor must be 0. And in fact, this gives us our second major behavior of capacitors in RC circuits. After a time much greater than RC, the fully charged capacitor will block all current through that branch of the circuit. which is just like if we simply replace the capacitor with an open circuit. Let's do an example. Consider this circuit. Now, when we first hook up this whole thing, this is actually identical to the circuit that we just talked about because we can ignore branches A and B. Their switches are both open. There will be no current through them. So these actually don't really participate at first. So we're left with a battery in series with a resistor and a capacitor. So just as before, immediately when we build this circuit, the current will be completely unimpeded by this uncharged capacitor, which means it'll be at t equals 0 as if R is connected directly to the battery. As time goes on, the current flowing through the circuit causes a charge separation across the capacitor, which impedes further current, and eventually the current diminishes and the capacitor approaches a final maximum charge of the EMF of the battery times the capacitance of the capacitor, and there will be no more current through this little branch. So then the next question we can raise is, what happens when we close switch A? Or what happens when we close switch B? Or what happens when we close both of them? Let's start by closing switch A, specifically a long time after we built the circuit, so that this capacitor has had time to fully charge. This implies that the voltage across this capacitor is actually equal to the voltage across the battery, right? Because this capacitor is balancing out the battery. If we think about it like the loop rule, like in the previous example, the loop rule tells us the voltage gained across this battery minus 0 voltage across this resistor with no current through it, minus the plus the voltage lost across this capacitor gives us 0. At the moment we close switch A, then, there's still no current through the left loop of our circuit. That's not the case in our middle loop, though. If we call the current through the capacitor I2 and the current through the resistor I3, then at the moment the switch is closed, our loop rule for the middle loop becomes the voltage of the capacitor, which is equal to the EMF of the battery, minus the voltage drop across the resistor in branch A. So the moment we close switch A, the current through that branch becomes the voltage of the capacitor equal to the EMF of the battery divided by the resistance R. But this current is caused by the capacitor discharging itself into branch A. And as the capacitor discharges itself, its voltage decreases, which means it will no longer be sufficient to completely block all current from the battery. And we're going to get more complex behavior where the battery will be able to push current through this resistor and then through branch A and so on. And eventually what's going to happen is the system will come to a new equilibrium. The capacitor will reach a new equilibrium charge that once again will block all current through the branch with the capacitor, but it will still allow current to flow around this loop over here. In other words, if we wait a very long time, this circuit is just going to look like this. The capacitor effectively removes itself from our circuit. A good question then becomes, what will be the final charge on our capacitor? The easiest way to approach this is if you look at this circuit over here, our capacitor is in parallel with this resistor. So I know that the voltage drop from here to here is the same whether I go across the capacitor or whether I go across the resistor. In other words, this capacitor is in parallel with this resistor. So if I can figure out the voltage across this resistor, the voltage across the capacitor must be equal to that. If I look down on my circuit down here, that seems like a pretty easy task. I have a battery hooked up to two equal resistances, and so each resistor in this case is going to end up with 1/2 of the total voltage of the battery. And that's also the voltage across the capacitor because it's in parallel with this resistor, and we can write that as Q over C for a final equilibrium charge of this capacitor of 1/2 times the EMF of the battery times the capacitance C. At this point, we could ask, well, what would happen now if I close branch B? In the short term, it's going to mess everything up. This capacitor being fully uncharged will allow current to pass through it no problem, which actually means there's no current would flow through this resistor at first. It would just completely go away, because why would current flow through this resistor when it can flow through essentially a short circuit? But as this capacitor charges up, that stops being the case, the currents are going to change, and eventually this capacitor will also reach an equilibrium where current will no longer be able to flow through branch B. If current is no longer flowing through branch B, then once again, after I've waited a very long time, my circuit will look like this, because no current will flow through this capacitor and no current will flow through this capacitor, which means it's as if we've simply removed these capacitors, according to the second behavior we discussed earlier in the video. Well, at that point, if I want to know, for example, what's the final voltage across this capacitor, well, it's in parallel with this resistor and with this capacitor, and so this will have the same voltage that they do. And because no current is flowing here, it is actually the same answer. The voltage across this capacitor is just equal to the voltage of the resistor in this circuit over here, which is 1/2 times the EMF of the battery. And so in the end, these two capacitors will end up equally charged, and they will each have a total charge after a very long time of 1/2 times the EMF of the battery times their capacitance. Figuring out what's going on in a circuit at the moment you hook up a capacitor to your circuit, or after waiting a very long time, is not a lot of work. We haven't done a lot of work on this page, and we've learned pretty much everything there is to know about the moment we close these switches, the moment we build our circuit, and after we wait a very long time. The tricky part is, what if I want to know what's going on in between? To investigate that, let's go back to the scenario where we just closed branch A. And this time, let's consider the scenario where just T is greater than TA. Not equal to, and not much greater, but just some short time after we've closed the circuit. What is our behavior going to look like then? In other words, I want to know, how are the currents and charges and voltages in the circuit changing over time after I close the switch? We need to label our currents. We have 3 branches, so let's call them I1, I2, and I3. The reason why I picked I2 to be pointing upwards is because I do know that the top plate of the capacitor will be positively charged and the negative plate will be negatively charged. And that means that it's actually reasonable to expect that once I open up this new branch, current will flow this way. The capacitor will push positive conventional current clockwise around this loop. But again, if I guessed wrong, if I labeled this current the other way, it just means I would end up with a negative sign in my math telling me that I picked the wrong direction. This gives us one single junction rule, which is that I1 plus I2 is equal to I3. There are also 3 possible loop rules. There's the left loop, the right loop, and the outer loop. We can pick any of the 3 possible pairs of these loops. I'm personally going to pick the left loop and the outer loop just because that minimizes the number of times I have to deal with the capacitor, which is really the most annoying part of this circuit. Right away from the 2 loop equations, we can see that Q over C has to be equal to I3 times R, because both equations start with E minus I1R, and both equations add up to 0. So this immediately gives us that relation, which is really just, we already knew that this capacitor is in parallel with this resistor. We can also substitute our junction rule into our outer loop rule equation to end up with this, at which point we have to do something about these currents. Well, the first thing to note is that I2 is the current through the capacitor branch, which means that I2 is related to the rate of change of the charge of the capacitor. If I2 is not 0, it means our capacitor is being charged or being discharged. The way I drew my circuit diagram, or the way I labeled my currents, I said that I2 is pointing upwards. Now, if I2 is going upwards, it means our capacitor is discharging. And that implies that dq dt is negative, which means I2 is equal to negative dq dt, because I2 should be positive, but positive means our capacitor is discharging, and so we have to insert that negative sign. We saw that in the previous video as well. I'm still left with two unknowns, Q and I1, so I'm also going to need to substitute in my left loop equation. That'll allow me to eliminate I1 in terms of Q. So let's do that, and then let's simplify it a little bit more. And finally, to actually solve this differential equation, we need to separate our variables. So all instances of Q are on one side and all instances of T are on the other. And finally, to solve for Q, we integrate both sides. We have to be very careful about the bounds though. For time, we can always just write it as 0 and T. We can just choose to start counting when we close that switch. On the other side, we have to be a little bit more careful because we don't start out with no charge. We start out with some initial value of charge, and we're ending up with some final unknown amount of charge. If you look back at about 4 minutes and 30 seconds into this video, you'll see that we already found that the starting value of the charge of this capacitor is equal to the EMF of the battery times the capacitance. The right-hand side of this integral gives us a nice straightforward T, some amount, whatever time after we close the switch. The left-hand side we can compute using U substitution. This is a very similar integral to some of the ones that I went through in the previous video, so I'm just going to go through it pretty quickly. The integral of 1 over U gives us a log. We apply the boundary conditions. We consolidate our terms. And we exponentiate both sides. One final rearrangement of terms gives us this nice expression for charge as a function of time. At this point, I actually realized that I made a mistake somewhere. When t is equal to 0, e to the 0 is 1. This gives us 3/2 times EC. But I should get just EC when t is equal to 0. So somewhere I lost a factor of 2. What this should really be is there should be a 1/2 there as well. I'm not seeing it. I've looked through my work a couple times and it's not jumping out at me. At this point, I'm tired and I want to move on. If you find where I dropped the 1/2, please let me know and I'll fix it. Qualitatively, this makes sense. When t is 0, we recover, assuming we can find this 1/2. I don't know where I lost it. We recover our initial charge before we close the switch. Then, as time goes on, this term becomes smaller and smaller, approaching 0, and we're left with half of the original charge, which makes sense because if we look at our circuit here, when this capacitor is finally returns to equilibrium again, each of these resistors will have half the voltage of the battery, which means this capacitor in parallel with this resistor will have half the voltage of the battery. And if it has half its previous voltage, then it should also have half its total charge. So qualitatively, that makes sense as well. Now, one other thing we can look at is that the time constant is different as well. We have a 1/2 in here, which means the time constant is smaller. That means it takes less time to charge up or less time to discharge. And one way you can think about that is this capacitor is no longer just connected with one resistor, but it has actually two branches that it can discharge into or charge from. And so the time constant of the circuit is also affected by that. In these kinds of problems, you'll note that the procedure for solving them is essentially always the same. You set up your junction and loop rules, you solve your system of equations until you're left with only one unknown. With an RC circuit, typically what that means is isolating your charge. And that means you want to end up with an equation that relates only to the charge on a capacitor to the current through that capacitor. And we can always relate the current through the capacitor to the rate of change of charge. That gives us a differential equation, which we can then solve by separating our variables, by rearranging it so that every instance of Q is on one side, every instance of T is on the other side. And then these equations will almost always result in an integral of the form du over u. The bounds might be different. The exact U substitution might be different depending on the circuit, but the procedure tends to be the same. And again, it's good practice when you arrive at your result, plug in 0 and see if your answer makes sense. For example, this half has to be here. I made a mistake somewhere. I know I did, because otherwise I do not get my appropriate lower bound. That covers what I had planned for this. Hopefully this helps you analyze RC circuits, and I'll see you next time.